Hello, my name is Ioan Nascu. I'm from Technical University of Cluj-Napoca, and I will present an auto-tuning method for alternating aeration control in activated sludge processes. In our days, we observe an increasing amount of wastewater and pollutant content due to population growth, accelerated urbanization, and economic development. And to solve this problem, wastewater treatment plants are necessary, which are complex physiochemical and biological processes. To control these processes, usually a hierarchical control system is used. For our paper, it's important the low-level control, that means the control at the process level, you can see here, where actuators, sensor, and the controllers are used. Why a control is necessary, we will explain later. First, we can observe here that the energy consumed for aeration in a treatment plant, it's about 60%. That means it's a lot of energy consumed by blowers to do tank aeration. To save energy is necessary to have a good control system and if it's possible, optimized control. Usually these plants have several tanks connected in series. You can see here 2 tanks, can be more. Anoxic tank and oxic tank. In oxic tank, we have aeration. That means air is introduced in the tank by blowers. Air is necessary to treat the wastewater. In medium and low plants, we can save space because here these tanks are succeeded in space. We can save space. We can use only one tank and we can have alternating aeration. To simulate and to test our method, we use the well-known simulation model BSM1, benchmark simulation model number 1, which is platform well known to simulate the wastewater treatment plant. And this platform was adapted and we introduced new blocks to make the connection between blowers and the bioreactor. Why control is needed for this process? Because if the process is well designed from, let's say, mechanical and hydrological point of view, everything will be well, but sometimes there are disturbances or perturbation in the input flow, in wastewater flow. So we have to adapt to new conditions. And there are constraints for the output of this plant, which is the effluent. Usually this plant operate with full aeration, which consume a lot of energy. And to save energy, we can control the blower's airflow. At the level process, controllers have to be well designed. What means to design a PID controller? Means to use a tuning method to design a controller, means to tune some parameters, which is presented here, proportional and integral derivative gain, which are 3 parameters, to determine this parameter or to tune the controller, we need the process model, we need the performance for the closed loop, and together this, using a tuning method, we can obtain the three design parameters. We do this by ourselves, or we can use an automated method, which is auto-tuning called. That means an algorithm based on the measurement for the process can compute the PID parameters and can tune the PID controller. As you can see here, we have two forms or the same controller, PID. This is textbook controllers form. In the left part, and in the right part, it's form used in practice. So we have to tune three parameters. We can see here the three parameters. We need the performances for the closed loop. That means steady state error 0 usually, and settling time, that means the time response for the process in closed loop for the controlled process. If we impose settling time, we can calculate this parameter, and we have in closed loop the model of the system. Using these two, we can compute the PID controller parameters. We have here formulas in the down part. You can see the mouse. Yes. And how to tune this parameter, but we need the process parameter. That means Kp, T1, and T2. It's a second order parameter. That means has a gain and two time constants, T1 and T2. To identify these parameters, we need to perform some experiments. Usually till now, using experiment, what kind of experiment were used? Connecting a relay in closed loop with the process. This is the process. This is a simple relay connected in closed loop will oscillate. So measuring the amplitude and the period of the oscillation, we can calculate the parameters. But from one experiment, we have two equations for the real and imaginary part. So we have calculate only two parameters. For three parameters, we need two experiments. In this paper, we present a possibility to use only one experiment. That means using an asymmetric relay. Using an asymmetric relay, oscillation will be also asymmetric, and we have two describing function, one for static situation and one oscillatory. From the static describing function, we can calculate gain of the process, and from the oscillatory describing function, we can calculate T1 and T2. So here are the formulas for Kp, T1, and T2. First these are the parameters of the process. You can see that here the calculations are based only on the measurements. B is depending only on the measurements and the parameters of the relay. A, B, M, everything here, you can see here the formulas depends only on the measurements and the relay parameters. So we can compute Kp, T1, and T2. Introducing this in the previous relation, we have finally the formulas to calculate the parameters of the PID controller. So we have here, this can be done automatic. You press a button and the auto-tuning procedure starts, and finally these three parameters are computed and fixed on the controller, PID controller. To evaluate this method, we do some tests. Here are presented two tests. One to modify the set point on the signal reference. It's here some modification step disturbances for the step point, and you can see here that the output of the process, which in our case is the dissolved oxygen in the aeration tank, follow the set point. Of course, I mentioned that we have intermittent aeration. So here it's aeration, here it's off, on, off the aeration. But when it's on, set point, the output reach the set point. Even if we modify the set point and looks well the output behavior. You can see here the output, and you can see here the input of the process. That means the flow of the air for aeration. And here you can see the output if some disturbances are presented in the input of the process. That here I think, yes, the flow, it's modifying flow of the influent. We have disturbances in the flow of the influent. You can see the output is constant, and the input, so the manipulated variable, is modifying to maintain the process output constant at the set point value, which here is 1.3. In conclusion, we need a well-tuned PID controller. Why? Because this mode of operation, that means intermittent aeration, has frequent step in set point. So we need an appropriate controller, well-tuned, to obtain good results. And our methods use only one experiment instead of two experiments. Also, we can modify the settling time of the process, as I presented here, the settling time of the process, which its T0 can be modified. And finally, good performance are obtained for the control of important parameter, which is dissolved oxygen in the aeration tank. If you have some question, and I thank you for. Okay, should I? Yes, sensors, the problem of the sensor in wastewater plant control, it's difficult because we don't have so many sensors. Fortunately for dissolved oxygen, we have a sensor now. It's not so expensive, about 1,000 euro, but you have to do serious maintenance to this sensor because it's optical, and the environment here, it's not so friendly. So you have to clean periodically and to calibrate periodically and to maintain it operational, because there is difficult environment here. But also for, let's say, organic matter, and for nitrates, for nitrogen, for all kind of this compound, is difficult to measure, and the sensors are very expensive. And okay, we try to use sometimes software sensor based on the other measurements, but it's not so easy. Thank you. Should I stop? F10?